Fermi level is a statistical distribution. It's a statistical number which is used to look at how these charge carriers are distributed within the band. When I say distributed, we know that we cannot precisely locate electron in one position. But we know there are X number of electrons and there are Y number of energy states in conduction band. So instead of exactly finding it, we create a statistical function and we say, okay, this function tells us probability of finding that electron in those all energy states. Look at this. We look at this class. We have 20 people in this room. Now, maybe 5 people have, I don't know, $1,000 in their bank account. 5 people have 500 in their bank account. 5 people have maybe 250 in their bank account. So it's just 20 people. If there are 20,000 people, instead of finding exactly how much money each one have, we say that's the average income or that's the average saving of this population. But I'll go counting, I don't know, or 4328. So we identify a population and we take some statistical numbers to explain whatever situation we are explaining, maybe savings, maybe income. So it's a similar concept here. So you have conduction band and we have energy states in there and we have electrons in there. So instead of exactly finding which electron is occupying which state, we come up with a statistical formula. And that's formula or that derivation is called Fermi-Dirac statistics. Two scientists who came up with this mathematical calculations to find where electron would be found in that band gap. And the theory that helped them or the concepts that they used is there are these three things: indistinguishability of electrons, which electron comes from which atom, we don't know, right? We cannot distinguish them. They have wave properties, which means they may be going in different directions. Going in different directions means they would have different energy associated to them. Remember the EK diagram? There was this minima of conduction band and minima of valence band both. So it's the same thing that would go here as well. And the third one is Pauli exclusion principle, which we know that no two particles can have same set of quantum numbers. Sorry about that. So these three theories come up and they define a function called Fermi-Dirac function. What does it tell us? It gives distribution of electrons over a range of these values. So, and when we get that, that's the equation we get. So what are parts of this equation? F of E is the function that tells us what are the probability distribution? What is the chance of finding an electron over these energy levels defined by E? E is the energy level. And the formula is 1 over 1 plus exponential of E minus EF over KT. EF is that energy level which we would define where it is located in the band gap. K is Boltzmann constant, and we are finding this distribution for a very specific temperature. Temperature can be 0 degree Kelvin, temperature can be room temperature, 300 degree Kelvin, right? So, but essentially the idea is that knowing that at 0 degree Kelvin, there is no electron jumping, and then they start jumping, and then you dope your surface, but still temperature has an effect of how many EHPs are there and how fast or what would be the energy an electron would have. So it has a strong dependence, exponential dependence over temperature, right? So once you define this relationship, we know a bunch of things. why we are talking about energy levels here? Going back to that Bohr's theory, every particle has energy. Every electron has some energy associated to it, right? And this does not account for the thermal energy. It counts for its own energy because it's rotating around a nucleus. Remember? So that energy is intrinsic to the particle. And so there are gazillions of electrons that have that energy and they belong to those energy levels. And that's where we calculated this energy level with E. And remember, there was used Planck's constant and all those things. And then comes the temperature contribution to this, which we are using to find out energy levels above which they will be filled and below which they will be empty. So now this relationship, if you plug in the values, you say, okay, if the energy level is right in the middle, so you plug in the values, you say E is right at EF. The energy level you're looking for is right at the middle. You get half. So half probability means flip of coin, right? So half probability means head or tail. Either it is empty or it's full. So at that particular level, it has half probability to be filled, which means above that function, the probability of filling it goes down. There's just that what is shown here. That below that value, there is more probability to be filled. Above that value, there is less probability to be filled. Now, what if we change the temperature? So if I add temperature, which means that levels would have an added effect of temperature, this probability function becomes a little bit relaxed, which means now there's more probability of having electron above the Fermi level, right? So maybe just a little bit more extra energy levels that can host electrons in there. You put temperature a little bit more, that goes even further. So we have now, if I just draw that line again, the original line, what we are saying is now maybe there are a little bit, a few more energy levels are available to host that electrons that will be coming from this side to this side, from valence band side to the conduction band side, right? Just because this relationship is getting better and better because this T is going up. So you can see qualitatively, if T goes up, and this is 1 over T, this value is going down, right? So which means this overall is going less than 2, right? And which means this whole number is becoming better than half. You guys agree with me? And this simple equation, which means the probability is increasing to have electrons on the higher side. And if we continue on that trajectory, keep on increasing the temperature, we have much more flexibility. And what I just did here is I've taken that same relationship and just rotated it 90 degrees. Just the same graph, but rotated it 90 degrees. Because a band diagram were made like this, so I want to put it on top of my band diagram. And when I do that, I see that this relationship can tell us exactly what are the chances of having electrons above certain center level. So this would be then something like conduction valence band and conduction band. We'll look at this on a coming slide. All right, so Fermi energy is the energy state whose probability of being occupied is exactly half. And electrons, they follow this kind of equation, this kind of statistical distribution, and we call it Fermi function. Same thing, straight from the book. Now, if I put it on my conduction band and my valence band, for equal number of electrons and holes, my Fermi level is right in the middle, which means same number of electrons, same number of holes. But now, if we add n-type, the number of electrons will go up, which means the Fermi level will go up, which means now there are many more energy levels available in conduction band because of this distribution function is more favorable to have higher probability of electrons. Now, if you look at the number, so that's the difference showing for that function. So if you do doping of p-type, this function is going closer to valence band. And when that happens, basically what we are doing is we are telling that there are less number of sites for electrons. And when you have less number of sites of electrons, we have more holes in that system. Now, in both these cases, the position of Fermi level is changing the probability of finding an electron in that energy levels. So less electrons, more holes, right? So we use Fermi level to distinguish how many sites are there in any given material, how many uh, charge sites are available in any material to host an electron or a hole. So when we are talking about distribution or we talk about statistics, if the probability of having one event is say X, the probability of having all the other events is 1 minus X. There's something which we did before as well, that if there is probability of having an activity as X, so the all other events are always 1 minus X because the total probability is taken as 1, right? So we use this to define a few equations.